we are here for second workshop of DevBits. In this workshop, we will be studying about recursion, graph, and dynamic programming. So let us start with the topic recursion. Before starting, तुम में से कितने लोग already CP करते हैं? और कितने लोगों ने first time start किया? Okay. So recursion. What is recursion? तुमको देखिए बहुत लोगों को आता होगा, but still will like go through the basic definitions of everything. So recursion, the process in which a function calls itself. A function recursively calls itself again and again. We call this process as recursion. So you might have used recursion already in many of your courses. So anyone here can give me an example of recursion? Very small or basic example.
Finding factorial.
Someone of you said finding factorial is very good example of recursion. So why we need recursion? Recursion, all those things what we do from recursion can also be done using iterative method. But why do we specially need recursion? Do anyone of you know? Like it is written there, I know, but
More efficient.
okay, so we need recursion because in many cases recursion makes our code very easy and like it reduces our code to one-line code, even two-line code from the iterative approach. Sometimes the iterative approach is difficult to write, to code, and even to like think of, to make the logic of iterative. In that case, recursion sometimes is very easy to write, easy to code, and easy to debug. So we need recursion. Recursion is helpful there. So we'll take an example now. Factorial of a number. So इसको आती है CP उसके लिए नहीं है, इसको नहीं आती है. Can you tell me how we can use recursion here? I don't need code or logic. I just need कि इसको recursively कैसे कर सकते हैं. Recursively मतलब like I'll write a function, but हमें use करना है कि वो itself को दोबारा call करें and something like that. तो आती है उसको तो आता होगा. It is easy. So every one of you know what a factorial of a number is. It is the number like multiplication of all the numbers from 1 to that number. So we can write n factorial as n into n minus 1 factorial. You all know this, right? So if we calculate n factorial using some function, then we can also calculate n minus 1 factorial using that function itself. So अब थोड़ा बहुत समझ आया कैसे रिकर्जन यूज कर सकते हैं. Okay, let's see the code. This is the code. We are using function to calculate the factorial of number n, and we will recursively call that function to calculate factorial n minus 1. So we don't like multiply the numbers here. We don't use iterative approach like multiply numbers from 1 to n and then show the result. We use that function itself to calculate n minus 1 factorial and just bring the result of n factorial. So there are two things here in recursion. I have written there. One is base case and the second is recursive call. What is base case? So base case is the case that will end your recursion. Actually, if there wouldn't have been the base case, what now could have gone?
Infinite.
If there wouldn't have been the base case, this function would have been an infinite loop. It could never end. It could just go on forever. So the base case is used to end the recursion, and the second is recursive call. So how is like the recursive call is the flow function. It is the it is used to calculate the value exact what we are trying to calculate. So let us see another example. Okay, how many of you know Fibonacci numbers already? Fibonacci numbers is a very famous series, and it is like denoted by the function fn is equal to fn minus 1 plus fn minus 2, and f0 is denoted as 0 and f1 is 1. So, you know how we can use recursion in this function? Like those who don't know, if you can think of how you can use recursion in that function. And it is clear from the function itself. It is very clear from the function itself that we can use a function that calculates the value of nth Fibonacci number, and we can recursively call it using the function of n minus 1 and n minus 2. So this is the code. The base case for n is equal to 0, and okay, so here it is a bit wrong. It should be for n equal to 0, it should be written 0. But the recursive call is still fine. This is the like you understand what wrong is in that function, right? So okay, see, this is the diagram for recursive calls of Fibonacci number function. So if we call the Fibonacci number for number 5, like here it is, so it will call for 4 and 3. Now now our motto is to calculate 4 first and then 3. Like we started from calculating f5, but now since the function like we jump to f4 and f3. Now in f4 itself we'll jump to f3 and f2, and then in f3 we'll go to f2 and f1, and like similarly in f2 we'll go to f1 and f0. So that branch will be calculated first, f5, f4, f3, f2, f1. So first at f1 will come to base case and f0 will come to base. Those two will return some value. F2 will be calculated from there. Then the f1 below the f3 will also be calculated because it will return from the base case. And similarly, like the f5 will be calculated in that way. So you have studied time complexity, right? In the first workshop. So anyone of you can tell me what what is the time complexity of this whole tree or something? Look in bit to form and correctly. You should I don't need the exact answer, I just need which type of time complexity will be logarithmic, linear, squared, or exponential. Any idea? Yes, it will be exponential. Let me tell you how it will be exponential. See, in this function, you can see Fibonacci n is calling for Fibonacci n minus 1 and n minus 2. So, for every number n, we'll have two separate function calls for n minus 1 and n minus 2. Okay, you understood this like what I said? For every integer n, we'll have two more function calls of n minus 1 and n minus 2. Okay, and this will go for every integer from 1 to n, because all these numbers will have to calculate first, then only we can calculate n. Understood? Like when we are calling for n, it will call for n minus 1 and n minus 2. Then n minus 1 will call for n minus 2 and n minus 3. So it will go down to like 1. Only at 1 it will return from base case. So for every number we have two more functions called, and we have n numbers. So we have 2 times 2 times 2 for n times. So the time complexity will be 2 to the power n. It will be of the form of 2 to the power n. It will have some constants also. So this was all for recursion. So if any one of you have any small doubt on recursion, you can ask. Till now, any doubt or anything you didn't get? Okay, so let's move on. Let's move on to graphs. So how many of you know graphs already? You studied. I don't think anyone will have studied. Is there anyone? So all of you are new to this topic. Nice. So a graph is a non-linear data structure which includes vertices and edges. So what this is the basic structure of graph. This is how we represent graph in diagrams. This is not how we represent in code, but this is what we mean by graph. So these are the nodes. This is the node. This is the node. This is the node, or you can say vertex also or vertex. And these are the edges. This is the edge. This is the edge. This is the edge. What does the edge mean is this edge is connecting this node and this node. It can represent anything in real life. It can represent a telephone line, a road, or a flight path, anything. And these nodes can represent real life structures as well, like telephones or cities or anything you like. You can see. So this is how we represent the graph. Like components of graph. See, this is what I told. This is how you represent a graph, and these all are nodes, the blue dot, and the lines are the edges. So there can be two types of edges. One is bidirectional edge, and the other is unidirectional edge. Okay, so I'll tell you. So like this edge, what I represented here, this edge shows that this node and this node are connected. But if I make this edge like this, what is the difference? Can anyone tell me? What did I just? So this edge shows that this node is pointing to that node. The difference being you can like relate unidirectional edge to a one-way road. Then you can only go from this edge, from this node to this node. You cannot go back from this node to like that. Otherwise, in the bidirectional edge, like this one, you can do both the things. You can go from this node to that, and from that node to that. So these are like the two types of edges we have in the graph. So how do we represent a graph in code? We cannot draw this in our coding language, so we have to represent some way. The very like common ways are adjacency matrix and adjacency list. We have one more way seeing it, and the very simplest way is adjacency matrix. So what does we mean by adjacency matrix? So an adjacency matrix will be a two-dimensional table. It will represent which and which edge has a node between them. So like this adjacency matrix is actually for unidirectional edges. You can have it for bidirectional edges as well. So see the zero here in everywhere there is a zero in the matrix represent that those two edges do not have a node between them, and one represents that they have a node between them, and it is unidirectional. See, like the zero is pointing to one. That means row for 0 and the column for 1 will have 1. But the column for 0 and row for 1 has a 0 because 1 is not pointing to 0. If it would have been bidirectional edges, then we would have 1 there also. So this is the very basic way to represent like the edges. But this is not very economical for us. Can someone tell me why? Not very useful. It is useful. We can use in many cases, but there are many cases where we won't be able to use this. So, like you understand how we create an adjacency matrix in code, because it is just in 2D matrix we can easily create ribbons in code. You would have studied it in the first workshop. Creating 2D arrays or 2D vectors, you can do it through them. But it is not useful for us. Like it is useful but not economical. Can you think? Yes. Yeah, the memory is yeah, so the reason is that if we have many number of nodes, the space complexity will increase and you won't have the memory to store that matrix. To counter that situation, we have adjacency list. So adjacency list is not very different from matrix, but let us see the code of matrix first. So this is how we can declare an adjacency matrix. So we have declared two variables and number of vertices and number of edges, and then we declared a 2D array of n plus 1 and n plus 1. Because like we are taking all those n square pairs, any one of them can have an edge. So then we took input and the input gave us u and v has an edge. So we declared like adjacency matrix of u and v should be 1 because they have an edge. And this is for bidirectional edges. For unidirectional edges, one of those statements will not be there. There will be the first or the second statement. That depending on like whatever you are taking. So this is how we declare our adjacency matrix. Now let us move on to adjacency list. So okay, before that what I'll tell you what an adjacency list is. So like in an adjacency matrix, all those zeros we are representing here, we don't need them actually. We only need the ones. Because we only need to know which two nodes have an edge, not which two nodes do not have an edge. Because it is clear from like two nodes can either have an edge or not have an edge. There is no partial case. So we don't need those zeros. We only need those ones. So can anyone tell me how can like we can neglect those zeros? Like it is tough to think of. Okay, so I will tell you. What we can do is we can store an array for 0 which contains the values 1 and 2. That represents the number 0 has an edge with 1 and 2. And another array for 1 which will contain the value 2 and 4. That will represent that the edge 1 has an edge with 2 and that node 1 will have an edge with node 2 and node 4. Similarly for node 2, 3 and 4. You understood this? What I just said? That we make 5 different arrays. Each array will represent all those nodes 0, 1, 2, 3 and 4 and the array will contain those nodes with which the particular node has an edge. Like the array for 0 will only contain 1 and 2 inside it, not 0, 3 and 4 because they don't have an edge. The array for 1 will only contain 2 and 4 inside, not 0, 1 and 3 because they don't have an edge. Similarly for 2, 3 and 4. Is this approach clear? So what we will save space using this, but it can also go to n square when all of the edges nodes have edges with all of the nodes. So we can have the same problem here when we have n square edges, but we don't generally have n square edges, so we use adjacency list quite often. So this is how we declare an adjacency list. So you have studied dynamic array vectors, right? So if we don't know which edge will have how many like which node will have how many edges. So we declare a dynamic array for every edge, for every node, declare an array of vectors. An array of vectors. That means we'll have n vectors and all those will be denoted as an array. We only earlier in adjacency matrix, what we were doing is you will have an array for node 0 and an array for node 1 and an array for node 2. What we now did is we have all those nodes here, but we have only a blank array on vector for all those nodes. Whenever we get a node for 0, we'll update it here. If 0 and 1 have a node, then we'll put 1 and then a blank space. And if 1 and 2 have a node, we'll put 2 here and then again a blank space. So we won't be using all that space that we were using here. It is similar to matrix, but the arrays are dynamic. That is the only difference. So that is why we use arrays of vector and not arrays of array. Is it clear? The only difference here is we'll push back in the list whenever we get a node between, an edge between U and V nodes. So it will only take the space of order of number of edges. So because every edge will be represented twice, so it will take less space than the electricity matrix. So we have another form of representation which is known as adjacency set. So you have studied set in first workshop, right? You know what a set is? You don't know any set. Anyone here who don't know this? Okay. So a set is a data structure which have its contents arranged in ascending order every time. Every time you insert a new object in the data structure, it will arrange all of them again in ascending order. So at every point, it will have its contents arranged in an ascending order. So if you create a set of integers, so they all will be increasing order at every point. So adjacency set is another form to represent graph. We use arrays of sets to represent adjacency set. I will show you the code, but I want to ask a question. The question like now all of you know set, and I have told you that adjacency set will be represented as arrays of set. Like we were using arrays of vectors there in adjacency list. Like I am declaring vector in adjacency list here, right? The only thing that will change is we'll declare it as set if. So what what will be the advantage of adjacency set? What extra feature can I get from adjacency set? Like I am getting all those features here also. We are saving the space. We don't need actually to store the nodes because there is no order of the edges. We know all the edges here also. Then why are we using adjacency set? There is a very minute operation. No, you are actually wrong because insertion is quicker in vector. Insertion is order of 1 of in vector and inside is order of log n.
किसी sorted array में values find करना easy होगा, faster होगा.
You are wrong here also because vector, yes, we can find it is both like order of log n. In vector you can also, it's sorted vector it is order of log n, but the statement is not wrong, it is right, but that is not actually what we are trying to do. We can use adjacency set for that purpose also, but that is not why we actually use it. Anyone can guess?
वेक्टर में कंटीन्यूअस स्पेस चाहिए, सेट में हम लोग कंटीन्यूअस स्पेस ही चाहिए ना.
हाँ ये मतलब ये हम यूज कर सकते हैं जब हमारे पास स्पेस की कमी हो. I don't think we have less space, but there is a very prominent operation that will be done easier using this, which is very heavy using the vector. Think of it think of the operations of set. What operations do we have in set? And we don't have in vector. We have that operation in vector, but it is costly in terms of time or space.
Vector में space double हो जाता है, capacity बढ़ जाता है और set में नहीं.
Space के हमारे पास दिक्कत नहीं. That is what he said. Space is not a problem. Our problem is time. Because we can have space, we can take RAM, we can buy more RAM, we can have bigger RAM, but we don't have time to make the code run for 20, 30 seconds. We don't have that. So I'll tell you, you know set arrays, set dot arrays. Is there anyone who don't know set dot erase? So set erase is a function that helps you erase an element from set, and it does that in log and time complexity. Vector erase is also a function, but it takes time complexity of order of n. So if we want to remove an edge in the adjacency list, what we'll have to do? We'll have to find that edge and we'll have to erase that edge. What time complexity will you take? Order of n. But in set, we can do that very easily. Like we have done that in the last two lines. We want to erase an edge between u and d. We can do that in very less time complexity with respect to adjacency list. So this is like the basic thing why we use adjacency set, because you are decreasing the time complexity by logarithmic values. It is very good for us in terms of time complexity. So like that was all how we represented graph. So now how we travel through the graph, how we search a node or an edge in the graph. So we have very like the famous two ways. First is depth first search and the second is breadth first search. So we will be studying on both of them. So the depth first search, the idea for depth first search is to pick a node and go in depth to that node until and unless there is any more vertices in that particular node that is not visible. So it is like tough to understand it, but I'll draw it.
We have a term called as root node or source node. Root node हम उसको बोलते हैं जो node which is of focus, like which node we require or something, like we have to do some operations from that. So this is assumed as a root node. So what we do in DevBits is we pick an edge, like we pick this edge, we go through that edge, reach that node, and then we won't come back to this vertex until and unless we have like traversed all the vertices that are connecting that are through this. So like we'll go through this edge, we'll visit all these vertices in some order, in some way, but we won't come back to this vertex until unless we have visited all three. This is the like basic idea of depth first search. We go into one edge and we visit all the vertices in that edge first. Then we go to the second edge. This is like very basic. We'll go to one edge first. We'll visit all the vertices that is included in that edge, and then only you can go to the second edge. You cannot jump to this edge until unless we have visited all these three vertices. So this is one of the ways to implement it. You can implement it in many ways. You will be seeing that. This is the code. I'll tell you what this code will do in this graph. So if you have a graph with like what we'll do is we have the root node as one. That we will pass to a DFS function initial. It will be that we have passed. It will be the root node 1. Then we'll either go to 2 or to 6. That is our choice. But we can do again, like let us take this one. So we went to 2. Then we'll either go to 3 or 4. We'll go to both of them, but first, like we went to 3, then we marked it as visited, then we came back to 2 because all the nodes that were So this is just a reversal. This is just a way how and like when you use it, you will see it in like.
Okay. So this is the application of DFS. The very basic application is finding cycle in a directed graph. So I have written is there is finding cycle in a directed graph, not an undirected graph, because undirected graph has infinite cycles. Like you can make any cycle, you can go to the neighboring edge and come back infinite number of times. So cycles are only in directed graph, not in a directed graph. So what is cycle in a directed graph? So cycle in a directed graph is a path from, like, you can come back to the initial position, traveling through that path. That is the cycle. Uh,
So like this. Okay, this is a directed graph. These all are directed edges. So in this graph, this is a cycle. This one. From 1 to 2 to 4 and 6 and then back to 1. So like we started from 1, 6 back to 1, so it is a cycle. Similarly, we can start from 2, 4 or 6 anywhere. So we'll come back to the position we will start. So this is what we call a cycle. So how we'll find the cycle using DFS? That is our question. So right. Visible है ना? ठीक है?
so this was the basic syntax of DFS. We'll have to change something inside this format. Can anyone of you like, try to think of or like tell what will you? Let me show you the DFS code first. This was the DFS code. Visited through will be there. Something inside the form will be changed. Any guesses? Try to think what will happen when you come back to a node that has already been visited. Okay, so let me just tell you first and right now. So like this is a cycle. You start like we start from 1, you go to 2, come back to 3, and then 4. So when we are at 1, we'll check, we'll see for 2. It won't have been already visited. We'll go there. So we came this way. Then at 2, we'll see for 3. It won't be visited. We go there. And for 3, we come back to 4. It won't be visited. We go there. When we are at 4, then when we see 4 has an edge to 1, but 1 will already be visited. Before we have even visited 1 from 4. Like this one here, we are visiting U from V. V was in the adjacency list of U. U was in the adjacency list of V. Then we visited U inside V, the loop of V. So what will happen here is, when we'll be at 4, we'll see that 1 is already visited. What does that mean? That we have come through this path, and that then only 1 will be previously visited. So we can check this. If we are at any node and the node connecting node connected to that node are already visited, that means we have a cycle in the directed ground. We can do here is, if visited I is 1, then this condition shows that cycle exists in a directed graph. This condition we cannot use for undirected graph. What will happen there if we use it for undirected graph? Like if this graph would have been undirected, what problem would have arose? See the difficulty when we visit 2 from 1 and check which all nodes have edges from 2. Then we'll count 1 in that node, in that in that case also. We'll see 1 and we'll see 1 is already visited. So we'll say that this is a cycle, which is like true, but this is not what we were trying to do actually. So that is why we said like the directed graph only a cycle, undirected graph as infinite cycles. Okay, so the next thing is bipartite graph. So bipartite graph is a very famous type of graph. It is a graph where you can divide all those nodes into 2 sets or say 2 teams. The condition being any 2 nodes that have an edge should lie in opposite teams. It is a very simple condition. We have a graph. We are trying to divide all those nodes into 2 teams. The only condition, if two nodes have an edge between them, they should lie in opposite teams. You understood the condition? Yes. Like what I just said here. The question समझ में आया कि question क्या है? Okay, मैं बता.
ग्राफ ठीक है हमें 2 टीम बनानी और भी create 2 teams we can create in any format like 1 2 3 and 4 this can be a team 1 2 3 and 4 this can be a team and this can the only condition is if two edges have a node, like two nodes have an edge between them, they should line up. Like where 1 and 2 has edge, 1 and 2 are lying completely. 2 and 3 has edge, but 2 and 3 are lying in the same team. So this graph is not bipartite. Bipartite graph की कंडीशन यही है कि अगर हम दो सेट्स में डिवाइड करते हैं और किसी भी दो नोड्स जिनके बीच में एज है वो ऑपोजिट टीम्स में लाई करते हैं देन दैट ग्राफ इज बाइपार्टाइट। बाइपार्टाइट ग्राफ क्या होता है मतलब किसी को हिंदी से दिक्कत है तो I think it is clear what is bipartite, right? So how we can do this? Not all graphs will be bipartite, but we will have to check if a graph is bipartite or not. So this is kind of your homework. I can tell you here, but it is easy.
You only need to do DFS, but you have to think of what the condition inside the DFS code will be. So it is kind of your homework. If we will share the code in the group. Okay, so if any doubt you have until now in DFS or before that, even in the question. Okay, so we'll move forward. DFS. So DFS is another graph traversing algorithm. The only difference in DFS and BFS is in BFS we will traverse the graph in levels. Levels with respect to the root node. So I'll tell you what
this is the root node which is lie on level 3. Okay. All those nodes which are directly connected to the root node will lie on level 1. So this node lie on level 1, this node lie on level 1, this and this. So this is like technically what I mean by level. So these four nodes will lie on level 1. And this node, and this node, and this node will lie on level 2 because they are directly connected to the node which are lying on level 1. And like we use the minimum level which is possible. Like this can also be said to lie on level 2, but we will not consider that because it is lying on level 1 before it is lying on level 2. So this node will have level 1, not 2, because it is directly connected to the level 0 node. And this node is directly connected to the level 1 node, so this will have level 2. This node will have level 2. The same reason, this node will have level 2, and this node will have level 3. So, like, you understood what I mean by levels. So, this is how we like mark levels in the graph. So, now we want to traverse the graphs in levels. Like, we want to traverse all the nodes first, which are in the same level. And in even in ascending order of the levels, we want to traverse all the nodes first which are in level 0, then all the nodes which are in level 1, then all the nodes which are in level 3. No, sorry, 2. Then we'll move to 3. So this DFS, using DFS we can do that easily. So this is the code. It is quite confusing. I'll tell you what all those things mean. So this is just a way to do it. You might come up with one of your own ways. It might traverse the same. It won't be wrong. This is just the way we do it, and I'm going to explain this. You can do it in any way you want. So, like, this is a very simple graph. You might have complex graphs, groups, and many things, but let us take simple example. So, what we do is, this is the root node. We use a queue. You might be doing what a queue is. If anyone let us not get a queue. level 0 node inside that queue first. So this I will present the queue here. So we put the level 0 node inside the queue first. Then what we do is we visit all the nodes, or we say like we put all the nodes that are directly connected to this node inside this. We did this. Like this is what the queue will look like at one point of time. This is the level 0 node. These three are the level 1 nodes. So we visited all the level 1 nodes after the level 0. That was what our condition was. So what we will do now is we'll remove this node from the queue. You know, like queue has the function to remove from start and to set the back. So we'll just remove this node from the queue. We removed it. So our queue will now look like this. So we'll take the first element of the queue and then we'll visit all the nodes connected to that element. So these are the three nodes. So we took two, we visited 9 and then we added to the queue. Then we remove 2 from the queue. Why we are doing it? I'll tell you. This is what the flow of algorithm is. I'm checking the algorithm. Then we put 3, we visited 3 and visited all the nodes that are directly connected to 3. Not 1 because 1 is already visited. It is also connected to 3, but we'll check which node is not visited and we'll visit that node also. So we visited 5 and 6 and we put them in our queue. And then I remove 3 from the queue. Then I visit 4 and I visit 7 and 8 and put them in the queue. And then I remove 4. So at one point of time my queue will also look like this. But if I suddenly remove these nodes, so this could have been my potential queue, or like you can store this format in some other array. So what this gives you? This is the level 0 node, these are all the level 1 node, and these are all the level 2 nodes. This is what we wanted to do, like visit all the level 0 nodes before all the level 1 nodes. Visit all the level 1 nodes before all the level 2 nodes. And if we had another more level, we follow the same way, like take the first element, then visit all the nodes that are directly connected to that element, and then remove it from the queue. This is what we are doing here. So forget about those like the visited distance right now. Okay, this is the source node, the root node that I said. We visited the root node. We took the parent of the root node. Okay, leave it right now. Then we push the root node into the queue. Then this is what we're doing for the algorithm. Unless queue is empty, take the first node, walk the queue, like remove the node from the queue, visit all the nodes of that node that are not already visited, and then push them into the queue. Mark them as visited also. You can mark them visited here also. It will be the same. Push them into the queue. Wait, student, I'll tell you what they mean. So, do you understand what we are doing here? Sorry, yes. This is the flow of the algorithm. This is how the algorithm is. This is not something. So, you understood like what we are doing to like why only using this method this will be possible. Like all the level 1 nodes will be visited before level 2. Is that thing here or नहीं किया तो बोल दो okay, like assume we are at some node. This is level 2, level 1 node, but assume it is some level x. So these will be x plus 1 levels. Okay, so when we are at this node, it will imply that we would have visited all the nodes before that level. X minus 1 and x minus 2, all that levels will be visited, and these like x levels will be in the level, take this, and we put these in the queue. Like we have some table there, we have X somewhere, and we have 4 somewhere, and then some other terms maybe there, and then we put 7 number. So this is very basic that you visited X before 2 other nodes of X. Okay, so you can like use the method of induction to clearly see that this was at X plus 1 and we go over here. So the X plus 2 will only be visited when we visit 7. So 7 से जो connected है वो तब तक visit नहीं होंगे जब हम 7 पे नहीं जाएंगे. तो 7 के बाद आएंगे. तो हर नोड पे तुम ये करोगे. 3 वाले तब तक visit नहीं होंगे तब sorry 5 and 6 तब तक visit नहीं होंगे तब 3 visit नहीं होगा. So these levels will come after that only. So that is what we actually wanted to do. And we ensured the same levels of sampling. Because how we are ensuring that, I'll tell you. So what we did for the root node was we took the level 0 node and then we took all the level 1. So like the other two, there are okay, there is only one level 0 node and there are like 4 level 1 nodes. So this is what we did. So all the level 1 nodes are now visited. So there won't be any node that is of level 1 and that is not visited. So now we can visit level 2 node in any order we want. That is not our concern. Our concern is the level 2 nodes will only be visited after level 1. We visit all the level 1 nodes. So all the nodes connected to these nodes will either be level 0 or level 1. Okay, so level 0 we have already visited. Now we visit level 2 nodes in any order we want. That is not a concern. The only thing we wanted is level 2 nodes should be visited after level 1. Okay, so अभी हम पहले लेवल एक लेवल के नोड सारे विजिट कर रहे हैं और कैसे कर रहे हैं वो हम फिगर देख रहे हैं कि एडजॉइंट ऑफ बी में जितने भी नोड्स हैं सबको विजिट कर लो. जो पहले विजिट देंगे पहले विजिट वही नोड्स होंगे जो उसके ऊपर वाले लेवल में मतलब उससे माइनस वन वाले लेवल में. ठीक है, तो उसके बाद के लेवल के सारे नोड्स हमने विजिट किए क्यू में डाल दिए. सिमिलरली मतलब ऐसे सारे लेवल 1 वाले नोड विजिट करेंगे कि करके ये नोड और फिर सारे लेवल 2 वाले नोड्स क्यों आएंगे और लेवल 2 ही क्यों आएंगे लेवल 3 क्यों नहीं आएंगे. क्योंकि लेवल 1 से जो डायरेक्टली कनेक्टेड है वो लेवल 0 हो सकता है लेवल 2 हो सकता है. लेवल 0 हमने विजिट कर लिया वो क्यों दोबारा नहीं आएगा. तो अब इसके बाद जितने नोड्स आएंगे वैसे लेवल 2 होंगे उसके ऊपर होंगे बट सबसे पहले लेवल 2 के आएंगे. तुम 4 लेवल 1 के नोड्स विजिट करोगे तो लेवल 2 के नोड्स ही मैच होंगे. लेवल 3 से कनेक्टेड नहीं लेवल 3 लेवल 2 से कनेक्टेड. जब तक तुम लेवल 2 के नोड्स विजिट लाइक लेवल 2 के नोड्स पे नहीं आते तब तक लेवल 3 के नोड्स क्यों नहीं आते. ठीक है, समझा कि कैसे वो फ्लो मेंटेन रहेगा कि लेवल 0 लेवल 1 लेवल 2 आ जाए. ओके, सो there are additional things in this code. One is the distance and one is the parent. I'll tell you what they mean. So this is the application of this. This is the very simple application of DevBits to find the shortest path from source vertex to all the other vertices in an unweighted graph. Okay, so this code is for actually the problem. So the distance vector in this code is representing the distance of the given node from the root node. Okay, so what we are doing here, so like the level I said actually represents the distance. Okay, what I meant by level was actually the distance of the node from the root node. Okay, I think it is will be clear from the level. Like all these are in level 1. That actually meant that in सबकी distance root node से 1 है. That is how we denoted, like how we define level, but you didn't know it before, so I took that. And all these will have distance 2 from the root node. This is all the nodes that are at level 2. Yes, that is what the level will take. So what we are doing here is like I get. So if like we have an arbitrary node, some n is there and some m is there, and this is like an arbitrary level x. तो जब हम इसको रिसेट करेंगे और हमारे पास इसकी डिस्टेंस है, ये रूट नोड से x डिस्टेंस पर है, तो and that x is the shortest path because that is important. This x distance is the shortest distance of this node from the root node. And it is at this level x and the distance is also x. So what can you say about the shortest distance of this node from the root? Assume it is not already known.
X plus 1.
Understood what I said? That there is a node n which is at level x, and the shortest distance of node n from root node is x. Now I am asking that a node m is connected to n which has not been already visited. So what will be the shortest distance of m from root node? Not n, root node.
X plus 1.
That is what we did. So same this. We are at node B. We are visiting all the nodes that are connected to B. We are denoting it by U. If it is not already visited, that means it is at a higher level than B. Then the distance of U will be distance of B plus 1. Okay. And the parent thing. So we visited. Okay. So if M was not already visited, and like you said, the shortest distance of M will be x plus 1. So the shortest path from M to the root node will include N or not. Shortest path. Like there may be another path, but one of the shortest path. There may be another path with the same shortest length, but one of the shortest path will include N. Because that is what we like declared earlier. जब हमने x plus 1 इसको बोला, हमने यही बोला ना कि ये shortest path, मतलब ये shortest x plus 1 होगा root node से, तो वो through n ही हो सकता है. किसी और के through नहीं हो सकता है. If there is some node q and जिसका distance x plus like 10 है, तो इसके through तो shortest path नहीं आएगा. n के through ही आएगा. समझा? कि हमने बोला कि लाइक ये इसकी शॉर्टेस्ट डिस्टेंस x है, इसकी x plus 10 है, तो इसके हमारे पास दो ऑप्शन हैं, अगर x plus 1 हो सकती है, x plus 11 हो सकती है. शॉर्टेस्ट कौन सी? x plus 1 है. तो x plus 1 अगर शॉर्टेस्ट है, तो हमने उसका पाथ निकाले तो q के थ्रू तो नहीं आएगा ना, वो n के थ्रू ही आएगा. तो हमने यही चीज यहाँ पे भी किया कि जब हम if that node is not already visited, like पहले से visited नहीं है और अभी हम विजिट कर रहे हैं, तो इसका शॉर्टेस्ट पाथ u का शॉर्टेस्ट पाथ थ्रू u b ही आ सकता है, किसी और नोड के थ्रू नहीं है. तो आप कंफ्यूज हैं, बट सबको समझ नहीं आएगा. किसी कोई दोबारा कर लो, कोई दिक्कत नहीं, थोड़ा कोई है इसको समझ नहीं है. आ गया था. So like we did three different operations there.
We did a PFS traversal. We we also stored all the distances, all the shortest distances of each node from the root node, and we also stored the path of shortest distance of each node from the root node. How will we get the path? That is a very good question. How will we get the path? हमने एरेस तो बनाए नहीं कि हम हर नोड के लिए एक एरे बनाते हैं और पाथ अल्फा प्रोबेबिलिटी है. हमने स्टोर किया है, मैं बता रहा हूँ हमने स्टोर किया है, बट हमको पाथ निकालना है. हम कैसे निकाल सकते हैं?
पेरेंट के थ्रू.
हाँ, पेरेंट के थ्रू क्या?
जैसे मेरे को नोड से किसी पर्टिकुलर नोड में जाना है, तो उस नोड का पेरेंट फिर उसका पेरेंट उसके पेरेंट ऐसे लिखना.
दैट इज द आइडिया. सो हमने बिल्कुल बेसिक पाथ स्टोर किया है कि हम U पर B से आए थे, तो हम B पर भी कहीं से आए होंगे, मतलब
like this line has a node E, there is a node U, and there is a node. So ये लाइन बताती है कि हम U पर B से हैं, U का पेरेंट B है, यानी कि अगर हम U के थ्रू रूट तक जाना चाहते हैं शॉर्टेस्ट पाथ में, तो हमें पाथ में D आएगा, तो हम B पर भी तो किसी और नोड से आएंगे। B अगर रूट नोड है फिर ठीक है, अगर B रूट नोड नहीं है तो हम किसी और नोड से आएंगे ना B पर भी, तो वो करंट ऑफ B में स्टोर होगा ऑलरेडी। दिस इज हाउ वी कैन गेट द शॉर्टेस्ट पाथ। हमें U से अगर रूट नोड पर जाना है, मान लो रूट नोड A है, तो हम U का करंट देखेंगे B आ, तो B आ गया, फिर B का करंट देखेंगे M आया, M आ गया, फिर अगर M का करंट A हो जाता है डायरेक्ट A देखेंगे, तो दिस इज द शॉर्टेस्ट पाथ ऑफ reaching the U node from the node A. समझ आया कैसे? We traverse all those currents until we reach the root node itself. So it did three things here. I think all these three things will be clear.
So आगे बढ़ते हैं। हाँ, what about the weighted graph? अब weighted graph क्या है?
और unweighted graph है। हम जितने भी ग्राफ्स पढ़ रहे थे, these are all are unweighted or say 0 1 weighted. What is 0? What I mean by that is like this edge and this edge are identical in terms of weight. Like if we say some priority of this edge and this edge, it will be the same. We won't say that this edge is like more has a more priority than this edge. But what if I say that this is a city A, this is a city B, and this is a city C, AB के बीच की distance 10 किलोमीटर है और AC के बीच की मान लो 50 है। So this is a real life situation. Real life situation में दो नोड्स के बीच में जो एज होती है उसका वेट भी है कि उनके बीच का 10 किलोमीटर का डिस्टेंस है, तो ये 10 किलोमीटर इस एज का वेट है कि वो उसके साथ आना चाहिए जब हम इस एज को कंसीडर करेंगे, एंड दिस 50 किलोमीटर इज द वेट ऑफ दिस एज। सो समझ आया वेटेड ग्राफ के। और 0 1 वेटेड से मेरा मतलब था कि लाइक ऑल द एजेस आर वन वेट एंड there is an edge between these two that has a 0 weight, that only. So this is a weighted graph. Weighted graph में edges में weights होते हैं जिनके थ्रू हम like some problems होते हैं, जैसे इसमें बहुत सिंपल प्रॉब्लम हो सकती है कि इसका वेट मान लो 8 है, इसका वेट 7 है, इसका वेट 15 है, और यहाँ पे कुछ ठीक है। हाँ, ये सिटी समथिंग f है, तो a से f में जाने के हमारे पास दो पाथ जो बिल्कुल दिख रहे हैं, a c and f, and the second path is A, B, and the third path is B, C, and F. So this is like a real life situation. कि हम A से C जा सकते हैं, C से F जा सकते हैं. That will cost us 58 kilometers of travel. This path will cost us 58 kilometers of travel. But इसका 10 मान 10. This way path will cost us only 35 kilometers of travel. This is like a basic real life. तो weights का यहाँ पे बहुत like weightage होता है जो हम shortest path का पहले करते हैं। हाँ, इसमें क्या दिक्कत है अगर हम DFS करें?
DFS से 58 आंसर है।
हाँ, DFS 58 आंसर है। बिल्कुल सही। तो क्या
मिनिमम पॉसिबल डिस्टेंस की तो 35 है।
DFS से तो नहीं निकाल सकते मिनिमम पॉसिबल डिस्टेंस, जैसे समझ आ रहा है क्या मतलब क्या कर सकते हो हम आगे के लिए अलग एप्लीकेशन। सो जो आगे एल्गोरिथम आएगी उसका यूज क्या है वो वेटेड ग्राफ से तुमने बताया।
We have dash 12. So transfer algorithm, what it does is it calculates the shortest distance, or you can even say shortest path of each node from the root node in a weighted graph. Unweighted graph में तो direct DFS लगा सकते हैं, DFS unweighted graph में DFS लगा सकते हैं, sorry. But उधर भी डायस्ट्रा लगा सकते हैं, आंसर सेम देगा. डायस्ट्रा is for weighted graphs. Weighted graph में best काम करेगा, and there is a condition there should not be any negative sentiment in the graph. ये मैं समझाऊंगा.
This was the condition to do. Right from हम करते हैं. This is the algorithm की ऐसी टेक्निक है कि we are in the root node. These are all the weights of all the edges. What we do is from the in VFS what we were maintaining was a queue. Right, we will also maintain a queue here, but we take the priority of the weights in that queue also. So अगर हमें A से उसके next level पे नोड विजिट करने हैं, तो हम किसी भी रैंडम ऑर्डर में नहीं करेंगे, हम उस ऑर्डर में करेंगे जिस ऑर्डर में उनके वेट्स हैं. तो हम पहले B विजिट करेंगे, then C विजिट करेंगे from A. मतलब बस इतना रन करें कि हम वेट्स की प्रायोरिटी क्यू में ऐड करें. कि पहले हमने A B इसलिए विजिट करा क्योंकि उसका वेट कम है, C का वेट इससे थोड़ा ज्यादा है. B हम ये बात मतलब दिस इज व्हाट द एल्गोरिथम इज. सो और यही चीज हम आगे करते रहेंगे. अब हो सकता है कि जब हम ये कर रहे हैं आगे जाके हो सकता है कि कोई ऐसा एज है जिसका वेट इसके भी आगे आना चाहिए, तो वो हम उसके आगे रखेंगे. लेकिन ये करना थोड़ा डिफिकल्ट है कि कैसे हम डायरेक्ट कैसे देखी हमें पहले बी ही विजिट करना है सी से, क्योंकि यहाँ पे मैंने दो ऐसे सिखाए हो सकते हैं 1000 ऐसे, तो तुम ऐसे चेक तो नहीं कर सकते कि हर एक ऐसे पे जाके देखो किसका वेट सबसे कम है उसको सबसे पहले विजिट करो. तो वी नीड अ डेटा स्ट्रक्चर टू डू दैट, लाइक जो अपने आप ही करना हमें करने की मेहनत ना पड़े कि हम ए से एक के साथ बी और सी बस विजिट कर लें, वो खुद से यहाँ ऑर्डर करते हैं कि इवन इफ मैं सी और बी उसको ऑर्डर दूं वो बना ही ऑर्डर देते. मतलब कि हम नहीं करना चाहते कि बी पहले विजिट करो सी को उसके बाद विजिट करो. हम किसी भी रैंडम ऑर्डर में करेंगे, वो डेटा स्ट्रक्चर खुद से बी से खुद से वो उस ऑर्डर में विजिट करेगा. So for that we use priority queue. Okay, so here is set. We can also use priority queue. Set तो मैं पता है set is क्या है.
So we are storing a pair in this. So you know pair. Okay, so pair is just an array with two numbers in it. So we are storing a pair. I am storing a pair. I'll tell you there also. And that pair, and we are storing that pair in a set. So what will set do? Set will arrange all those numbers in their priority. That is what like set do. जैसे हम कोई नया नंबर डालेंगे, हो सकता है हम उसको सेट बहुत लेट रिकॉग्नाइज किया, बट उसको सेट के फ्रंट में आना चाहिए. तो सेट अपने आप वो काम करेगा, हमें करने की जरूरत नहीं है, वो उसको फ्रंट में रहेगा, उसकी प्रायोरिटी सबसे हाई रहेगी. So like we started with inserting the distance of the source node, which is 0, and the source node inside the set. So this is one way to implement the algorithm. We can implement this algorithm using priority queue also. You know priority queue. The priority queue is like just the queue which does the work of set, but it does like the opposite of what a set does. When you insert elements inside a priority queue, it arranges them in this order. That's it. It's a queue. You can insert element at टेक आउट फ्रॉम द फ्रंट, बट वो बैक का इंसर्ट होता नहीं, जैसे तुम उसके अंदर इंसर्ट करते हो वो डिसेंडिंग ऑर्डर में अरेंज हो जाते हैं सारे एलिमेंट्स दोबारा से जैसे पहले, और फर्स्ट एलिमेंट तुम इजीली एक्सेस कर सकते हो. सो यू कैन do this using priority queue also. So what so let us while loop में हमने क्या किया है, until and unless the set is empty, similar to what we were doing in the BFS, until and unless the queue is empty, we take the first, like we if you s dot begin text second, s dot begin arrow, इसका मतलब मैं समझा देता हूँ. सेट के अंदर पेयर स्टोर हो रहा है, ठीक है. तो पेयर में फर्स्ट और सेकंड दो टर्म्स होते हैं जो फर्स्ट और सेकंड एलिमेंट्स को डिनोट करते हैं. तो एस डॉट बिगिन एरो सेकंड मतलब होता है कि सेट के बिगिनिंग एलिमेंट का सेकंड एलिमेंट इन यू में स्टोर कर देंगे. दिस इज व्हाट द लाइन मींस. समझा? पेयर यूज किया है तुम लोगों ने पहले, मतलब किस किसने नहीं किया है आज तक पेयर यूज नहीं किया सी प्लस प्लस में, समझ किया है? ठीक है, फिर तो समझ आएगा होगा. तो एस डॉट एलिमेंट एस डॉट की दिस टाइम विल बी क्लियर स्क्रीन. फर्स्ट एलिमेंट जो हमने ऑलरेडी यूज कर लिया उसको रिमूव करने पड़ेगा. फिर हम उस एलिमेंट के सारे एजेस में गए. हाँ, इसमें थोड़ा सा चेंज होगा एडजेसेंसी लिस्ट में. एडजेसेंसी लिस्ट में हमें वे एजेस प्लस उनके वेट स्टोर करने पड़ते हैं, क्योंकि अदरवाइज हम वेट मतलब तुम मैप में या किसी और स्ट्रक्चर में भी स्टोर कर सकते हो, बट दी लाइक मोस्ट कॉमन इम्प्लीमेंटेशन है to change the adjacency list and store pair in the adjacency list. You can see it is the second line. I have declared a vector pair index of 100 length. That denotes कि pair के first जो first element होगा वो होगा कि इसके नोड होगा, नोड की वैल्यू होगी, and the second element will be what is the weight of that edge. Okay. So then what we did is we went inside the like adjacency list of U, we check all the pairs. Okay, the if condition here I'll explain it. If distance of V dot first is greater than distance of V dot second plus distance of U. इसका मतलब कोई भी कर सकता है. Like हम अभी V नोड पे हमें U के ये चेक करना है, सॉरी उल्टा बोल गया, हम अभी U नोड पे हैं, हमें V के लिए चेक करना है. V एक्चुअली नोड डिनोट नहीं करता है यहाँ पे, V एक्चुअली वो पेयर डिनोट करता है एज का, किसके साथ नोड है एंड उसका वेट क्या है. तो V डॉट फर्स्ट इफ किसके साथ नोड है, V डॉट सेकंड इफ उसका वेट क्या है. So we check like the node V dot first could have been already visited. वो हो सकता है कि पहले विजिट होगी, बट हमें उसका मतलब नहीं है. हमें मतलब है कि क्या हम U थ्रू U उसको विजिट करते हैं तो उसका जो ऑलरेडी पाथ आया था उसके शॉर्टेस्ट पाथ आता है नहीं आता. जैसे नो सुनता
like this is a graph. हमने जब A विजिट किया होगा तो हमने B और C विजिट किए होंगे, ठीक है. तो यानी C का डिस्टेंस हमने 20 नोट कर दिया एक पॉइंट, हमने B का डिस्टेंस 1 नोट किया होगा और D का डिस्टेंस हमने 5 नोट किया होगा. एंड जब हम B पे होंगे तो हम दोबारा से C विजिट कर सकते हैं क्योंकि D C के एडजेसेंसी लिस्ट में होगा. तो हम ये चेक कर रहे हैं कि हमें अभी ये मतलब नहीं कि हमने उसको पहले विजिट किया है, क्योंकि हो सकता है हमने बहुत बड़े पाथ से किया हो, हमें दोबारा करना है. तो हम ये चेक कर रहे हैं कि डिस्टेंस ऑफ V डॉट फर्स्ट इज दिख रहा है एक कोड जो यहाँ पे लिखा हुआ है, बता रहे थे ना. से अपडेट करते तो क्या डिस्टेंस आएगा 8 कौन सा बेटर 8 तो हम एक देयर इज अ लाइन अगर दिखती है तो साथ वो डिनोट करती है कि if distance of the node we are trying to visit is greater than distance of the node we are at plus the weight of the edge then we'll update the distance of the node we are trying to जो नोड हम विजिट करना चाह रहे हैं उसका प्रीवियस डिस्टेंस जिस नोड पर हम हैं प्लस इन दोनों के बीच का जो एज का वेट है उससे ज्यादा है तो हम उसको दोबारा विजिट करेंगे क्योंकि लाइक हमारे पास उसका कम डिस्टेंस है तो वो बेटर है हम दोबारा विजिट क्यों कर रहे हैं उसका भी रीजन है हमने बी विजिट किया था सी विजिट किया तो हमारे क्यू में बी और सी रहे होंगे तो हो सकता है हम किसी पॉइंट पे एफ विजिट कर रहे हो सी के थ्रू तो इसका डिस्टेंस 26 स्टोर हो गया बट क्या डिस्टेंस सही है डिस्टेंस गलत है क्योंकि सी का डिस्टेंस ही गलत था तो जैसे हमने सी का डिस्टेंस चेंज किया हमें एफ जब उसके नीचे अगर कुछ भी हो सकता है बहुत बड़ा मतलब ग्राफ के नीचे कनेक्टेड हो तो उन सबका डिस्टेंस चेंज करना पड़ेगा दोबारा से तो हमें सी को रीविजिट करना पड़ेगा वो हम ये कोड में जो लिखा पढ़ने वाला है जो नोड हम विजिट करना चाह रहे हैं उसका डिस्टेंस अगर करेंट नोड प्लस वेट से बड़ा है तो हम उसको दोबारा विजिट करेंगे तो ये लाइन की वैल्यू है मतलब एक्सेस नहीं है कि हो सकता है जिस पॉइंट पे हम इस नोड से इसको नया विजिट करना चाहें तो ऑलरेडी हमारे सेट में था ना बट सेट में हम गलत वैल्यू स्टोर की उसकी 20 वैल्यू स्टोर रही थी सेट में पेयर स्टोर करते हैं और उस पेयर में एक सेट के पेयर में हम क्या स्टोर कर रहे थे यहाँ पे दिख रहा होगा कि डिस्टेंस ऑफ द नोड एंड द दोनों स्टोर कर रहे थे तो किसी पॉइंट पर हमने सी स्टोर किया होगा तो सेट में हमारे पास सी के लिए 20 एंड सी स्टोर ना होगा ये गलत है तो गलत है ना तो हमें एक्चुअल में स्टोर क्या करना है 8 एंड सी तो इफ देयर इज एनी प्रीवियस अकरेंस ऑफ दैट नोड तो हमने उसको रिमूव किया हमने उसका डिस्टेंस अपडेट किया एंड हमने उसको दोबारा से स्टोर दिस इज व्हाट वी तो मेरा कहीं भी कोई डाउट है नेक्स्ट if there is like another way to do this
मेरा टाइम में तो है आगे भी टॉपिक से टाइम लगेगा तो वो मैं बता दूंगा अगर किसी को इसमें कोई डाउट है अभी तो पूछ लो अदरवाइज मैं दीपो हूं से पूछ लो ओके सो we'll have a break of 5 minutes after that we'll start dynamic programming so